Welcome to our presentation on SoundHapticVR, a project focused on creating head-based spatial haptic feedback for making sounds in virtual reality accessible for deaf and hard of hearing users. Virtual reality systems rely on spatial audio to convey critical information such as source localization, notification, ambient sounds, and many more to enhance the immersion and realism. However, these audio cues are often inaccessible to deaf or hard of hearing individuals, significantly limiting their VR experience. Several previous work have addressed sound localization for deaf and hard of hearing users using different approaches. Some key projects like SoundHapticVR, EarVR have explored visual and haptic feedback respectively. Among various approaches, we were interested in haptic-based approach to convey sound information through the skin as a feedback location and free up the visual and auditory channels. Also, using the head as a location for tactile communication is effective due to superior signal transmission in the bone tissues of the skull. Building upon previous work and limitation, our research is guided by three main questions. 1. How do tactile sensitivity threshold for deaf and hard of hearing users vary for different positions on the head when using a VR headset? Second, what is the ideal configuration or arrangement of the transducers on the head for effective tactile-based localization of sounds in VR? Third, how well does the system convey sound source information through audio tactile transducers? To address these questions, we designed a head-based haptic system that converts audio signals into multi-channel haptic feedback through actuator based on 4 different regions on the head with VR headsets. Here is the architecture of our prototype. We built a multi-channel audio processing system that runs on the laptop. This system drives the 4 haptic actuators placed on the VR headset to send spatial haptic feedback on 4 different locations on the head. The hardware component includes 4 voice coil actuators, 2 Bluetooth stereo audio receiver boards, a 3D printed case made of PLA material to hold the circuits, and cushioning to hold the actuators. This setup is designed to attach the head strap of a Meta Quest 2 VR headset. The software component includes real-time audio processing local servers built using Python and a Unity VR app that streams head tracking information and sound information to the Python server. A custom planing algorithm is used for the localization effect. The preliminary study aimed to determine the maximum perceivable tactile frequency threshold on different head regions for deaf and hard of hearing users using the SoundHapticVR system. 12 participants engaged in a psychophysical study using the method of limits to identify these thresholds at 4 different head positions, which are left, right, front, and back. This is an example plotting from single participant. The line chart shows the frequency threshold across multiple trials with 4 different positions. The threshold for the front is the highest, around 600 Hz, and the lowest is for back, which is around 500 Hz. The right error bar chart describes vertical lines, and the dashed vertical lines represents the minimum perceptible threshold of 516 Hz. The result indicated that forehead, which is front, had the highest sensitivity, while the back of the head has the lowest sensitivity. This helped us to determine the haptic feedback frequency range to be used in the subsequent studies for our setup. The second evaluation focused on effectiveness of 4 different actuator configurations on the head for localizing sound sources. The 4 configurations are left-right back, left-right front, and left-right front back. The participant performed sound localization task in VR with each configuration. Infinite single-tone sound of perceivable frequency is used as a stimuli. The video describes the gameplay of the VR task where the participants are trying to select a sphere where they feel like generating a sound. This is the data visualization of the accuracy and task completion time results from study 1. The figure 1 is the bar chart of the mean selection accuracy in percentage across different configurations, along with the standard deviation. And the second figure is the box plot of the mean task completion time accuracy for both correct and incorrect selections in seconds across different configurations. The dotted line represents the average mean task time for both correct and incorrect selection. The results showed that the left-right front configuration had the highest frequency, which is 89.91%, and was preferred by the participants due to its ability to provide clear directional cues without causing sensory overload. The left-right setup had the lowest accuracy and had longer task completion time with frequent front-back sound confusion. The left-right back configuration caused confusion due to lower sensitivity in the back and a blurred sensory feedback between back and side regions. The study concluded that adding a front transducer significantly improved localization accuracy, making the left-right front configuration the most effective. Study to assess the usability of the left-right front configuration for identifying different sound types in virtual reality environment. 13 participants performed tasks to locate and identify sound sources in a closed VR room using distinct haptic patterns. The results showed higher accuracy for distinct haptic patterns and some challenges with similar patterns, especially when they are placed close together. This spectrogram shows the audio tactile tracks used in our study, highlighting the difference in patterns and intensity for each sound types. The study found a overall higher accuracy in task completion, with participants demonstrating improved performance over repeated trials. Sounds with distinct and strong haptic patterns like waterfall or a gunshot are easier to identify, while similar patterns pose most challenges. Participants found it easier to recognize patterns resembling real-life vibrations like a ringing phone. They also mentioned that the front actuator helped confirm sound sources, especially when objects were closely placed. The study confirmed that SoundHapticVR system could effectively convey various sound types through haptic feedback, enhancing accessibility for deaf or hard of hearing users. For more information, please do check out our paper. Thank you for attention and cooperation.